Does God exist? Are science and faith enemies? Your host for this series was an atheist who became a believer in God through his studies in science. Here is public high school teacher John Clayton.
We've been looking at a logical sequence of ideas that have to do with questions about creation. We've seen that there was a beginning. We've seen the beginning was caused. And we've been looking at what the cause is. Is the cause blind, mechanistic, opportunistic, rote, mechanical chance? Or is there intelligence in the creation? We've looked at it from an intuitive standpoint. We've looked at it from an architectural standpoint. Another way this can be looked at is by something which has been called irreducible complexity. That actually was a term coined by a man by the name of Behe in a book called Darwin's Black Box. Dr. Behe's discussion had to do with biochemical systems, which I frankly don't feel qualified to function with or to deal with. But I think there are other places where that idea can be used. And if you wanted to state it a little more simply, you might put it something like this. When numerous things have to be right, and by that I mean it have to be exactly the way they are in order for things to work, the likelihood of chance being the cause of that is essentially zero. In other words, the idea is that when you're looking at something that has incredible complexity to it and you start looking at things that are interdependent, your probabilities become extremely remote. Now, let me show you how, as a physics teacher, I would prefer to approach this. Here are a couple of equations that kids learn in any elementary physics class. Normally, it would be 10th or 11th grade in high school. The first equation that you're looking at is an equation for gravity. F is the force of gravity. M1 and M2 are the masses of two objects that attract each other gravitationally, and X is how far away they are. Now, in order for that equation to be true, in order for it to work, there is a constant, a proportionality constant, which is called the universal gravitational constant. And we've written the value on the screen, 6.67 times 10 to the negative 11th. In order for an atom to exist, the force of gravity has to be within certain limits. If you change that numerical constant by any small amount, modifying the equation and the force of it, an atom couldn't exist. If gravity is too large, matter tends to collapse into a black hole. If gravity is too small, matter tends to fly apart. Another equation that kids learn in an elementary physics class when they study electricity is called Coulomb's law. F, again, is the force, but this time it's the electrical force between two charged objects, like an electron and a proton. Q1 and Q2 are the values of the charges measured in coulombs. And X is how far apart they are. It's an equation that has the same form as the one for gravity. And again, there's a constant, K, 9 times 10 to the 9th. Now, if you change K, you have problems with matter. If K is too large, then particles that have the same charge would be repelled too quickly. If it's too small, they wouldn't be repelled enough. The value of K is critical. And by the way, lots of interesting stuff here. I mean, if you compare the value of G in the gravitational equation with the value of K in the electrical equation, you can understand why we have electric motors and not gravity motors. But what's important is to understand that these constants all work together along with the third equation, which has to do with the force due to motion, to allow such a simple thing as an atom to exist. A hydrogen atom with a proton and an electron, that cannot exist unless those numbers are within a certain range. Now you say, well, you got two equations, two numbers, that's no big deal. Well, it's not just two equations with two numbers. There are magnetic constants. There are coupling constants. There are nuclear constants. As a matter of fact, there are 47 different constants, like the two that I've shown you, that have to be exactly what they are. And like Behe's work with biochemical systems, To suggest that somehow these could happen by trial and error, by some kind of a chance process, is not a workable solution. And you can apply statistics to discussions of this type. There's another kind of design which has been referred to as the soft anthropic principle. Now, philosophy students will recall that there are all kinds of different anthropic principles, hard anthropic and soft anthropic, and there's all these different sorts of things that can be argued. But let me give you sort of a Claytonized version of the soft anthropic principle. We're just simply saying that when you look at the creation as a whole, when you look at what it takes to sustain life, and when you look at life itself, is chance a viable mechanism to explain the creation as we see it? Let me try to share with you some of the things you run into scientifically in a discussion of this type. And let me emphasize here that if you don't understand all of the scientific evidence that I'm about to throw at you, that's not significant. You'll understand most of it, and your kids will understand it. The young people will have no trouble with this at all. The point is that I just want you to get a handle on the kinds of things that are present. You're looking in the picture right now on the screen at a galaxy. And this is a galaxy that's like our galaxy, which is called the Milky Way. What you may not realize is that our galaxy is a special type of galaxy. It's a spiral galaxy. It's called a spiral galaxy type B. Now, what that means is that the arms of our galaxy are wound with medium tightness. What that means is that there's lots and lots of interstellar material in our galaxy. Lots of stuff to make planets out of. Lots of stuff to make life out of. But did you know that that kind of galaxy is very rare in space? 80% of all galaxies in space, numerically, look like this. They're called elliptical galaxies. They have no interstellar material. There is nothing to make a planet out of. There is nothing to make life out of. How could you have life in a place with nothing to make it out of and nothing to put it on if you had it made? And that's 80% of all galaxies in space. Some galaxies, like this, which are called irregular galaxies, have enormous disruptive explosions occurring in them. And separate galaxies just blow up every so often. As we look out into space with our deep space telescopes, we see wide ranges of different types of galaxies, many of which do not contain the right chemicals, the right aged materials, the right systems to enable life to be able to sustain. And some astronomers are saying that having the right kind of galaxy, very well the probability could be as low as 1 in 100. Now that's just an example of the kind of parameter we're talking about. Let me show you another one. This is a sketch from a graduate textbook in astronomy showing our galaxy, looking at it from the edge. Now, if you look at our galaxy from the top, it sort of looks like a fried egg sunny side up. But if you turn it over and if you look at it at the edge, just like looking at a dinner plate, it would look perhaps a little bit like this. The green areas in this picture are places where there's too much matter for a stable solar system to exist along that plane. The gravitational forces, the tidal forces would pull the solar system apart. The red areas are places where the galaxy is too hot, too active. Black holes exist there. A great deal of activity goes on in that part of the galaxy. You could not have a stable solar system in that area. As a matter of fact, for a stable solar system to exist, it would have to be in the dotted lines called axial gravity lines. Now, as you look at this next picture, you'll notice that we've sort of extrapolated that to let you see where these would be. There is a habitable zone. Recently, in several science periodicals, there have been discussions about habitable zones. There's a habitable zone for a solar system above and below the equatorial plane of a galactic system. And in order for a stable solar system to exist, it has to be in one of these zones. Now, how could you use that to calculate the probability, by chance, of being in the right place in the galaxy? Well, that's very simple. You just calculate the volume of those two donuts that are in the picture and divide it by the volume of the whole galaxy. And scientists have calculated that the size of those habitable zones might be as large as 12 cubic light years. But the volume of the whole galaxy is like 15,750,000 cubic light years. You could talk 12 out of 15,750,000. Okay, file it away. We'll be right back. This is a picture of the sun. And actually it's showing the sun in different ways with what's called a hydrogen alpha picture. We talked about that in the very first video that we presented to you. Other pictures showing the dynamics of the sun. And I'm sure you've seen cross-sections of the sun, showing what we understand about its magnificent processing equipment that enables us to have a very stable and very consistent star that supplies the needs that we have around us. Even though the sun goes through prominences and sunspots and sometimes does stir our atmosphere, it's still an incredibly tame, quiet, proper star. But if you look up in the sky at the Pleiades, what you'll see is a group of 7 stars, the 7 sisters, that are microwave emitters. These are stars that are extremely hot, extremely active, have all kinds of X-rays and other types of radiation that would be catastrophic for life. As a matter of fact, blue hot stars are totally and completely without the ability to sustain a living system. Recently, as astronomers have looked out into space, they've not only seen these types of stars, but they've also seen that most stars in space are red stars. Recent Hubble data has shown percentages that are way up in the 90% range of the fact that stars are dwarf stars. They're red dwarfs or K dwarfs. They're stars that are very, very small. A star of this size and of this coolness would be unable to sustain a functional solar system. And some red stars are too large. Betelgeuse in Orion is so large that you could put our whole solar system inside it. There couldn't be a stable solar system around a star of that magnitude. Many stars are flare stars. Many stars are pulsating stars. We now know that over 90% of the stars in the sky are binaries or trinaries, 2 or 3 stars orbiting each other. Our students do a lab in high school in which they plot the luminosity of stars against the temperature of stars. It's called the Hertzsprung-Russell diagram. There are literally thousands of stars that you can plot on that diagram, and a microscopic percentage of them could sustain any kind of a functional solar system. Some astronomers are saying the probability of having a star that could sustain any kind of life-bearing planet are perhaps as low as 1 in 25 million. And there's one kind of star that just blows your mind. And it's not the big blue star that you see in the background in this picture. It's that thing in the foreground. This is an object which is sucking the life out of that big blue giant star as it swings it around. It will eventually take that big blue giant star, which is 1,000 times larger than our sun, and it will crush it to a mass the size of a thumbtack. If you could shine a flashlight by this thing, the beam of the light would be caught in that vortex you see and would be spun into the center and ultimately just disappear. As I'm sure most of you know, it's called a black hole, a space-going vacuum cleaner that absorbs anything that gets anywhere near it. And these aren't just hypothetical things. They're not just things that make good science fiction stuff. We actually have a photograph of a black hole made in recent times. And the black hole in this picture is not the white thing that you see in the center. That's a star being destroyed as it funnels into the center. The black hole is off to the right. But the diameter of this thing, the accretion disk, is like the diameter of the Earth's orbit around the sun. And remember, it takes us 365 days to go around one time. This material orbits once every 12 hours. So we can calculate the mass at the center. This is a scary object. But you know something? You have lots of things you can worry about tonight as you go to bed, but being swallowed by a black hole is not one of them. The closest black hole is in the Northern Cross. It's called Cygnus X1 Beta. It's 8,400 light years from the Earth and poses no threat to us whatsoever. But what are the mathematical probabilities of being a part of space with no black holes? We've discovered hundreds of them in the last year or two. And every time one is discovered, it says again how unlikely it is that by chance you could have a functional solar system. Now you can go on and on with this. You look at planets and you see that they have to be the right distance from the sun. There is a habitable zone that a planet has to be in order for life to exist. Many planets are too small. They can't hold a gaseous atmosphere. Many planets are too large. They have too big of an atmosphere. As a matter of fact, recently we have learned something interesting about our own solar system. We all know that there have been comets that have been seen in recent years going by the Earth and going around the sun. What many of us may not realize is that these comets could be extremely dangerous if they hit the Earth. As a matter of fact, some years ago there was a comet, the Levy-Shoemaker comet, that looked like it might actually hit the Earth. But do you remember what happened to it? As it tried to get to the Earth, it had to go by Neptune and Saturn and Uranus and Jupiter. And remember what happened? Jupiter reached out as it came by and grabbed that comet. It ripped the Levy-Shoemaker up into 17 different pieces, which you see here. And several years ago, you could have sat in your living room and you could have watched as one of those fragments slammed into the surface of Jupiter. And the fireball was larger than the diameter of the Earth. Would have been catastrophic if it had hit the Earth. But you know what we have found as we have modeled this system? We now know that our solar system has 4 comet sweepers. Neptune, Uranus, Saturn, and Jupiter, that make it essentially impossible for a comet of any size to come in along the ecliptic and get to the Earth. What are the probabilities of being a part of space with 4 comet sweepers? We could go on and talk about the tilt of the Earth on its axis. We could talk about the magnetic field of the Earth. We could talk about the question of what our moon does. There's a book that was written a couple of years ago by Neil Cummings, the head of the astronomy department at the University of Maine. It's titled, "What If the Moon Didn't Exist?" And what he shows is that in a very short time, the Earth would become inhospitable if we did not have a moon, which stabilizes the tilt of our planet. You thought the moon was just for lovers. Well, it's good for that. But it has an incredible function in the structure of our system as a whole. And this process can go on and on. I teach astronomy. I could give you, I bet I could list 50 to 100 different parameters like this. And as we have discovered new planets going around other stars, we have seen even how unlikely the system is when you compare it to other systems. Because we now know that most of those systems seem to have very large planets that are very close to their stars. And the eccentricity of their orbit, how far out they swing and how close in they come to their stars, is usually much different than the nice circular orbits which we tend to have in our own solar system. But let's do a little probability study here. What I've done in this chart is I've listed some probabilities that I have seen in different writings of scientists and astronomers and people who are interested in this that suggest what the probabilities might be. By chance, from the Big Bang, of having the right kind of planet in the right place with the right conditions to have life. Now be careful here. You know, there's an old saying that says figures don't lie, but liars figure. And I think it's important to realize that when you look at this, what we're trying to do is to isolate values that don't lend themselves to this. And just to make it really easy, let's take each of these numbers and just simplify it. Let's just say that each of the things that are listed on the screen right now has a probability of 100. 1 in 100. And we're just going to use 10 of them in this particular situation. What are the odds? You may not need this, but just to make sure we're all on the same page, let me show you a little statistical lesson here. I have a deck of playing cards in my hand. 52 cards in a deck. And in this deck, I have an ace of spades. Let's suppose that I were to shuffle up the deck very, very well. And I were to say to you, okay, I want you to draw the ace of spades out of the deck. And you reach in there and you pull a card out. What were the probabilities that this would be the ace of spades? Yeah, sure, 1 in 52, we all understand that. Now, suppose I shuffle up the deck and I say, okay, this time I want you to draw the ace of spades twice in a row out of this cold deck. I hold out the deck, you pull the ace of spades, I put it back in, shuffle it up, and you draw it a second time. And we say ahead of time that's going to happen. What are the odds? And if you know anything about statistics, or if you sell insurance, or if you've ever played the lottery, You know the answer to that. It's 1 out of 52 times 1 out of 52. When you have two things that have to be right, you multiply the individual probability. So that's 1 chance out of 2,704, right? Now let me show you how fast this goes up. Suppose I said to you, okay, this time you're going to do it 4 times in a row. 4 times in a row. I hold up the deck, you pull the ace of spades. I put it back in, shuffle it up, you draw it again. I put it back in, you draw it again. I put it back in, you draw it again. 4 times in a row. You pull the ace of spades out of a cold deck. What are the odds? 1 out of 52 times 1 out of 52 times 1 out of 52 times 1 out of 52. That's 1 chance out of 7,311,616. And if you don't believe me, multiply it out. Now you say, okay, so now you told me how to win the lottery. What's this got to do with anything? Well, let's go back to that list of variables. See, it doesn't do any good to be in the right kind of galaxy if you're in the wrong place in the galaxy. It doesn't do any good to be in the right kind of galaxy, the right place in the galaxy, if you're going around the wrong kind of star. It doesn't do any good to be in the right kind of galaxy, the right place in the galaxy, going around the right kind of star, if you're too close to that star. Because if you're too close to that star, you're going to burn, baby, burn! And if you're too far away, you're going to freeze. In other words, just like this deck of cards, everything, every number that you talk about has to be multiplied. Now, if you multiply 10 1 out of 100s, what do you get? And remember that we've only talked about a microscopic number of variables that are available. Because if you were to go down and list all of the things that scientists know, and this has been done, books have been written by atheists and scientists who are not atheists, that show that the probabilities are beyond the number of subatomic particles in the cosmos. And not just a little bit beyond the 10 to the 70th, which Dirac and others have talked about being the number of subatomic particles in the cosmos. I mean, we're talking numbers like 10 to the 700th power. And those kinds of numbers say to us, the universe is not statistically possible by chance. Now, the response of the atheist to this statement will be something like this. Well, if it's possible at all, ultimately it's going to happen. Yeah, I understand what that statement is saying, but let me make a point to you. If you jump out of an airplane at 10,000 feet with no parachute of any kind, the odds of your survival are 1 in 10 million, according to the American Parachute Club. 1 in 10 million. Now let's just suppose that I were to reach in my pocket and I could pull out $1 million. A nickel's not close, but let's suppose I did that. If I say to you, if you'll jump out of an airplane 10,000 feet in the air with nothing on but your birthday suit for $1 million, would you do it? And see, I think all of us would readily admit we would not jump out of an airplane at 10,000 feet with the probabilities of 1 in 10 million for any amount of money. But the probabilities of the cosmos occurring by chance is so much greater than that. I mean, we're talking 176 million times greater than that. If you wouldn't gamble your life for odds of 1 in 10 million, for any amount of money, why would you gamble your eternal soul on a probability that is 176 million times less likely than what you already admitted you wouldn't take on your life? See, I suggest to you that the evidence says that the probabilities of chance being a viable mechanism are so ridiculously small that no thinking, logical person would be willing to accept it. I would like to suggest to you that we have these numbers and the basis of the numbers available to you, and you can contact us if you'd like copies of them. But I would also like to suggest to you that this is not stuff put out by creationists or by material who have an axe to grind on these issues. The people who are working with this, the scientists who are doing the research, are the ones that are saying these explanations, these probabilities suggest to us that there is intelligence and there is purpose in the creation. We've already talked about the statements that have been made by Frederick Hoyle, by Albert Einstein. And I would suggest to you that we can statistically and logically show that there is a personal God that is responsible for the creation. Now, let me also suggest to you that all we talked about in today's discussion, in this particular tape, is talking about the odds of getting a rock in the right place. How about life on that rock? You can start with the Stanley Miller experiment, and you can look at the work of Behe, or for that matter, Francis Crick, and you'll see that they show that the statistical odds of going from the Miller experiment to life is way beyond any reasonable probability that could be explained on the basis of chance. The soft anthropic principle says it is statistically impossible to believe that chance is a valid mechanism for the world in which we live. May I remind you again that the Bible says we can know there is a God through the things He has made. And the challenge that we have today is to look at the creation around us and to deal with the question of creation. And I believe if we do that, we see that the heavens declare the glory of God and the firmament show His handiwork. But there's one last challenge I'd like to mention, which will be the subject of our next presentation. Because an atheist would say, well, if you're going to say that this whole thing is design, then why is it so screwed up? Why is there disease? Why is there death? Why is there cancer? Why is there AIDS? Why is there war? Why do we have all the awful things that are present if in fact God created the heavens and the earth? And I believe the problem of human suffering is something that we need to look at and deal with. And we'll do so several times in this series of presentations. But in our next video, we want to look in a somewhat superficial way, but for just a few minutes, at the question of whether the problem of human suffering is in juxtaposition to the statement that there is intelligence and design in the creation. We hope you'll join us for that discussion.
Does God Exist is an educational program which attempts to provide evidence that man can logically believe in God and that the Christian system presented in the New Testament is the best option for successful living. We offer materials free and on loan. Contact us by mail, fax, or email for a catalog, to request materials, or just to ask questions. Does God exist may be the most important question you will ever ask.